Welcome to this seminar on multi-motor unit analysis. The needle EMG examination may be divided into four parts. Insertional activity, where the needle is moved briskly by a few millimeters in the tested muscle when the patient is relaxed. Spontaneous activity, this is assessed when the patient is relaxed and the needle is not moved. The insertional activity and spontaneous activity give useful information about the excitability and stability of muscle fiber membrane. It also gives information about hyperexcitability in the motor neuron or the nerve fiber. In the third step, the patient produces a slight contraction and maintains it. The needle position is adjusted to record sharp EMG signals, and they are used for assessment of so-called motor unit potentials, or the MUAPs. And finally, the patient increases the force of contraction gradually to reach maximum effort. This is used to assess the number of motor units, their activation, their firing pattern, and so on. In this webinar, we are going to focus our attention on analysis of motor unit potentials. The EMG examination is often performed in a subjective manner. One looks at the EMG waveforms, one listens to their sound, and comes up with a conclusion about the normal findings or any abnormal things that one may find. Quantitative analysis is slightly different. It is more objective. One records the EMG signals using standardized conditions. And now that we are talking about motor unit potential analysis, most often the analysis is done by using a concentric needle. The low frequency setting is set to 3 Hz, and the high frequency setting is at 10 kHz. As I indicated earlier, this needle is manipulated to record sharp potentials, and usually one accepts potentials that are greater than 50 microvolt in amplitude. The norm is to record 20 different motor unit potentials. And having recorded these waveforms, one proceeds with making measurements. Measurements such as amplitude, duration, phases, etc. And having made the measurements, we compare them against reference values. And there are two ways of making this comparison. One is the so-called outlier approach, where one looks at a single measurement and defines whether it is normal or outside the normal limits. The second approach is to calculate the mean values of measurements and then compare them against appropriate normative data. So quantitative analysis is more intense. It involves more work, but it is not as much work as we think. My analogy would be to use a calculator. If you had a simple problem, multiply 5 by 3, you don't need a calculator. You can do it on top of your head. Now, if you had a more complex problem, a more detailed calculation, such as shown over here, we could do it manually, but perhaps using a calculator will get us the correct result faster. So, whatever we can do in subjective assessment, we can also do by quantitative analysis. Quantitative analysis is just a faster method in certain problems. So why do we want to do quantitative analysis? Many will argue that we have been doing EMG subjectively and it has worked quite well. Of course, once you get experience, you can recognize certain abnormalities and you can do a lot of analysis subjectively, no doubt about it. But what happens when the abnormalities are mild? They are subtle. So this is where quantitative analysis can be quite useful. Sometimes you may want to document abnormalities. In certain areas, there may be medico-legal cases where they want objective evidence of abnormalities. So quantitative analysis is one way to offer it. Many times in patients with myopathy, you want to select a muscle for muscle biopsy. And sometimes a needle EMG can be useful. If you find some abnormalities on needle EMG, then you can say perhaps this muscle may be suited for performing a muscle biopsy. We can compare findings on serial investigations. So this will be useful to study the progression of disease. And this is used mainly for research purposes. It is important to note that the findings on quantitative analysis is the foundation of subjective assessment. One may argue that I never do quantitative analysis, I do everything subjectively. But that knowledge that was given when a person is taught subjective assessment actually comes from quantitative analysis. The rules of analysis were based on quantitative analysis. And in my opinion, when we know quantitative analysis, it gives us a better appreciation of signal abnormality. We can recognize subtle abnormalities. So I think knowing and practicing quantitative analysis makes one a better electromyographer. Just to go through history a little bit, quantitative motor net potential analysis was pioneered in 1940s by Professor Fritz Buchthal, and he used to do everything manually. It used to take several hours to study just one muscle. In 70s, we got the access to so-called amplitude trigger, delay line, and averager. It was much faster. We could select individual motor units, we could average them, clean them up, remove noise, interference, etc., and make measurements. But even with that, it used to take about 20 minutes per muscle. Now, given the time constraints in a busy clinical EMG laboratory, that's a lot of time to spend on examining one muscle, and that has been the primary reason why many move away from quantitative analysis. They think it's a very time-consuming process. And as we will see in this seminar, that's actually not the case. In the 80s, there came an algorithm which is called automatic decomposition EMG, or ADEMG. It was developed by Professor McGill and Dorfman, and it used to be available exclusively on the Nicolay system. And this algorithm would analyze a 10-second epoch or a slightly longer epoch in about 45 to 60 seconds. It would decompose it, and it would give you 4, 5, or even more motor net potentials that were contained in the signal. So that was a significant improvement, but still 45 to 60 seconds was a lot of time to wait. So there was the concept of multi-motor unit analysis. The goal over here is to make the analysis faster and efficient, but at the same time, it should be kind of similar to the subjective assessment. We don't want to invent a new tool. We want to complement the subjective assessment. And this idea and development came simultaneously. There were two groups who worked on it. Nandedkar and Barkhaus in US, and Stolberg and Koverses in Sweden. And they shared their ideas. So the multi-MUAP analysis algorithms developed by these two groups are fairly similar. The important thing to remember here is that now it takes less than a second to analyze a 10-second epoch. Remember, in ADEMG, it would take 30 to 60 seconds. So by reducing the analysis time, the method becomes fast. And now it takes less than 5 minutes to record and analyze 20 motor net potential. Remember, earlier I indicated that it is customary to record 20 different waveforms for quantitative analysis. So what used to take several minutes is now less than 5 minutes. So the multi-MUAP analysis is indeed a very efficient way of signal analysis. And with interest in this technique, normative values are also available. They have been published mainly by Professors Stolberg and co-workers Nandedkar and Barkhouse have also given some normal values. The important thing is that the values are available for biceps, deltoid, and first dorsal interosseous muscle. They represent the C5, C6 root. They also represent the C8 root. So these are the typical radiculopathy screens that you may want to do in the upper limb. They are also available for the tibialis anterior and vastus lateralis muscles, which are essentially L2 to S1 roots. So although the number of muscles that have been investigated for normal values is small, they actually represent the more common muscles that are tested. Professor Stolberg and colleagues have also investigated other muscles, but the published data in literature is available for these muscles. Now that you have an idea about how multi-motor unit analysis evolved since 40s, if you want to call it, here is what we are going to study in this seminar. I'm going to teach you about some basic concepts of anatomy and physiology, motor unit and motor unit potential. We will talk about measurements of motor unit potential. We will look at the different recording techniques, including the ones that I have just mentioned. We will discuss how the abnormalities are assessed. So let's start with the motor unit. A motor unit consists of all muscle fibers innervated by one motor neuron. So a muscle has got thousands of muscle fibers. They are organized into motor units. The motor neuron is located in the spinal cord. And when the motor neuron discharges, it is activated voluntarily. It produces an action potential that passes through the motor axon, through the terminal axon branches, and arrives at the end plate or the neuromuscular junction. The action potential is transferred to the muscle, and the action potential propagates to both tendons. The action potential initiates the electromechanical coupling, causes the contraction of the muscle fiber, which generates the force, and the electrical activity is recorded on the electromyograph. And in the context of recording from a single motor unit, we will call it a motor unit potential. So the motor unit potential is the electrical activity recorded from a single motor unit. A motor unit potential is the summation of action potentials from all fibers in a motor unit. Let's look at what a motor unit looks like. So the muscle fibers that are innervated by one motor neuron are distributed randomly within a roughly circular territory of 3 to 10 millimeter diameter. And there is considerable distance between fibers, often more than 300 micrometers. The muscle fiber diameter is relatively uniform, though there is some variation. So this is the architecture or the cross-section of a normal motor unit. Now let's see what would happen in a patient with myopathy. So here is a region where we have lost muscle fibers because of disease processes. Here is a region where we have increased variability of fiber diameters. Some fibers have become atrophic, some have become hypertrophic. Here is a region where we have regeneration of muscle fibers, splitting of muscle fibers. So we have a cluster of muscle fibers. So think about an orchestra. On the left-hand side, we have got people sitting uniformly on the stage. So they will produce one kind of sound. And on the right-hand side, some players have walked away. Some people have decided to move in a different area. Some want to play very softly. They are feeling weak today, and some want to play very loudly. So that's going to change the sound of music. And we can easily hear that this is not the way the orchestra normally sounds. And that's exactly the concept in the motor unit potential analysis. With normal motor unit, we have one kind of waveform for the motor unit potential, one kind of sound. And in myopathy, that sound and waveform is going to change different because of this reorganization or remodeling of this orchestra. So this is what happens in neuropathy, where the disease is mainly in the nerve or in the motor neuron. So we have got two motor units, a red one and a brown one. And the brown motor unit dies, and this is called denervation. And this will produce spontaneous activity like fibrillations and positive shock waves, something that I discussed earlier. That's the step 2 in routine EMG. And the denervated fibers then get picked up by the surviving motor units. This is called renervation. So now we have a different organization of the orchestra. We have got more players, and they're placed very compactly. And again, that's going to produce a different kind of music. So here are examples of the waveforms. We can see a normal motor unit. It's a very simple shape. And then in myopathy, the duration is rather short and the waveform is more complex. And in the nerve injury, we can see even more complexity to the waveform. At the bottom, we can see myasthenia, where the waveform keeps changing from one discharge to another. And on the right-hand side, we can see from motor neuron disease, the potential is very big, and it has got some satellite potentials. So this is the way the abnormalities in the motor unit architecture are manifested in motor unit potential waveforms, and that forms the basis for analyzing the MUAPs. So the MUAP analysis is very useful to locate the primary site of lesion. One of the key questions in the EMG examination is this myopathy or is this neuropathy? Where is the lesion? Is it in the nerve or the neuron, or is it in the muscle? And this is something that is easily addressed by motor unit potential analysis. It is also useful to study diseases of neuromuscular junction. By looking at motor unit potential, we can also tell what is happening in the motor unit. Let's say a patient had nerve injury and now they are undergoing renervation. We can see this phenomenon based on something called stability of the motor unit potential waveforms. And we can also comment on the severity and prognosis. So motor unit potential analysis is an important part of the routine EMG examination. And therefore, whatever we can do quantitatively will certainly be a plus. Let's now look at how to perform motor unit potential analysis. And I will start with a very simple scheme. This is the manual motor unit potential analysis. This is the way Professor Buchthal described it in 1940s. We insert the needle, we adjust the position to get sharp potential. The patient is giving slight contraction and maintaining it. Here is the signal. It is sharp and crisp. So we are going to record this signal for some time, and then we will freeze it on the screen, and then we will analyze it. I think we got sufficient time over here, so I'm going to pause it. Professor Buchthal gave a very simple rule for identifying motor unit potentials. He said, if you find a waveform that repeats and you see it 3 times in a very short period of time, that's a motor unit potential. So let's see how many potentials can we find over here. Here is a waveform. And once again, notice that it's a very sharp, crisp signal. It rises very quickly. This is called a short rise time. So here is the waveform. Here is it again, and here is it again. So we have seen it 3 times, so that's a motor unit potential. Here is the second motor unit potential, here and here. And here is the third motor unit potential. Professor Buchthal gave some simple measurements. The amplitude is measured peak to peak. Now in this case, my calibration is 200 microvolts per division. So let's look at this signal. This is about 2 divisions. 2 multiplied by 200 gives us an amplitude of 400 microvolts. If we look at this signal, this is about 1 division, so that's 200 microvolts. This is a little bit less than 2 divisions, so maybe 350 microvolts. So amplitude is very easy to measure. The phases is a measure of how many times the signal changes polarity. So let's look at this potential. It goes below the baseline, so that's phase 1. Now it's above the baseline, so that's phase 2. Now it's below the baseline, so that is phase 3. So this potential has 3 phases. And you can see this potential also has 3 phases. This one has probably 2 phases. Professor Buchthal gave simple rules. He said if the potential has 4 or less phases, then we will call it simple. If it has 5 or more phases, we call it polyphasic. So we have simple potentials and we have polyphasic potentials. And finally, we can measure the duration, which is the time from when the potential starts, so somewhere over here, to when it stops somewhere over here. This potential is about 1 division or slightly longer. The calibration is 10 milliseconds per division, so the duration of this potential is a little bit more than 10 milliseconds. Duration, in my assessment, is the toughest parameter to measure because you rarely get a nice clean baseline like this. You often get some disturbances along the baseline from other motor units, noise, interference, and so forth. So this is the way we can look at motor net potentials. Let's continue with this recording and let's look at another portion in this signal. How many motor net potentials do you see over here? Well, the correct answer is 1. Here is a potential. I can see it here, here, and here. I have seen it 3 times. So that's a motor net potential. If you look at the other waveforms, they are not repeating, so they cannot be considered as motor net potentials. They are actually superimpositions of the waveforms that we saw earlier. And superimposition can often generate waveforms that look abnormal. So for example, if you look at this potential, this has got 1 phase, 2, 3, 4, 5. So that's a polyphasic potential. And here is a polyphasic potential, and so forth. So you have to be very careful. You must identify waveforms that repeat. Now let's look at another method of identifying motor net potentials, and that is based on using an amplitude trigger and delay line. So let's see this recording. This is the pre-running. The motor net potentials occur anywhere. So now what I'm going to do is turn on the trigger. I'm going to set up an amplitude level, which I'm going to control. And the system is going to show me the signals only when that amplitude level is exceeded. And as a result, the discharges of that signal will be time locked on the screen. So let's go with it. So this is my trigger level. I'm close to baseline. So that's no good. Notice that discharges of this motor net potential are now time locked. They appear stationary on the screen, so I can see them very easily. I'm going to move the trigger level up. Now I'm triggering on the other motor unit potential, and this waveform is time locked. So this is the principle of triggering. Triggering allows us to superimpose discharges of potential, which makes it very easy to recognize the repeating waveform. In the triggered mode, we can also change the time base. It's 3 milliseconds. And we can superimpose the potentials. So here are 3 discharges. I'm going to superimpose them. And upon superimposition, we find that we have hardly any change in the waveform. So this is what is called a stable potential. So this is the way the motor net potential analysis was done in past. And even now we can do this in our routine EMG study. We can freeze the screen, we can look at motor net potential, we can trigger on individual motor net potential waveforms and look at their measurements like amplitude, etc. Now, let's look at multi-motor unit analysis. As I indicated, the concept behind multi-motor unit analysis is to support your subjective assessment. So whatever signals that we see on screen, we want to be able to analyze them quickly so that we can appreciate and interpret them better. Now, this is what happens. On top, you can see the EMG signal, and the first step in multi-MUAP analysis is to filter it. Use a high-pass filter. So we increase the low frequency setting. That stabilizes the baseline and allows us to look at the sharp component of motor net potential. The computer program then applies a trigger level, and this is used to identify the so-called the discharges or possible motor net potential discharges. And finally, we use template matching algorithms. So we look at this waveform over here. I will put it in this box. I will take this waveform, compare it with the first box. That's not the same. So I'm going to put it over here. I look at the third one, it's not the same as first or the second, so I will put it over here. And then I look at this waveform, Well, it actually matched this one, so I will keep it here. And this one matched over here. So this is the way template matching is done. And when you have sufficient matches, we feel confident that this is a motor unit potential waveform, and then we can average it and analyze it. So this is the multi-motor unit analysis display in 1992. You can see the individual discharges in superimposed mode. They look like they have been triggered, which makes it easy to assess their waveform. And the white trace is the averaged waveform. Here is confirming the analysis. This is the EMG signal in the free run. You can see the motor unit potential numbers over here, and we can also see them in the boxes. So how do we perform quantitative analysis using multi-motor unit analysis? We record signals with sharp and crisp sound. It should contain discharges of 1 to 4 different motor units. It's okay to have a little bit more. Having one only, it's not very nice. It is going to take you more time. So perhaps 3 to 4 is a better way of recording. We sample several sites separated by a few millimeters, collect about 25 to 30 motor unit potentials. Then we review the motor unit potentials. We exclude potentials that are noisy, duplicate. If they are marked incorrectly, one may also make changes to the waveforms manually. And then we analyze the mean values of MUAP measurements like mean amplitude, mean duration, and we can also analyze the individual MUAP measurements using the outlier criteria. Let's discuss a little bit more about the reference values. So here are some data that has been reported in literature, on the top by Professor Stolberg and co-workers, at the bottom by Professor Barkhouse and co-workers. So over here, we have the normative data for mean value. So here is the way it is done. You study a muscle, record 20 potentials, measure amplitude of every MUAP, and then take the mean value. So in one subject, the value could be 450. In another subject, it could be 600. In another subject, it is 700. So you take all of this data and calculate the mean. So for the deltoid, that was 550, and the standard deviation was 110. Now, in general, a 2 standard deviation band about the mean is considered as the normal range. So 550 minus 2 standard deviations. 2 standard deviation is 220, so the lower limit is 330. 2 standard deviations up, so you take 110 multiplied by 2, so that's 220 plus 550, 770. So what this means is that if you record 20 potentials, measured amplitude of each potential, took the mean of it, in a normal muscle, that should be between 330 and 770. And same way, we can look at the duration criteria. The mean is 10.4, standard deviation is 1.3, which gives us a normal range of about 7.8 to 13 milliseconds. So this is the way one can assess abnormalities based on mean values. The other approach is based upon outlier, and those limits are indicated in the yellow over here. What it says that if you record 20 motor unit potentials, 18 out of 20 should have amplitude between 162 and 1531 for the deltoid. So you're allowed to have 2 potentials outside these limits. But if you have 3 potentials outside that limit, then that study becomes abnormal. Sometimes you will get 3 abnormal potentials within the first 7 or 8 MUAPs that you study, so at which point you can stop investigation. So outlier is a very fast way of looking at data, and it is particularly useful when the abnormalities are obvious. When the abnormalities are mild, one probably needs to look at the mean values as well as the outlier approach. And similarly, here are the normal limits for duration, 4.2 to 18.4 milliseconds. So those are the 2 approaches, mean values and individual values. Phases are analyzed in a slightly different way. As I indicated earlier, a potential is called polyphasic when it has 5 or more phases. So in this case, the polyphasic potentials are identified with the yellow highlight. In a normal muscle, usually polyphasic potentials are less than 15%. Here we have 20 motor unit potentials, and we have 4 polyphasic potentials, so that's 20%. So in that sense, this is abnormal. Let's look at some more examples using mean values. So here are 20 motor unit potentials. We have measured amplitude and duration. The mean amplitude is 491. The normal range is 330 to 770. So the amplitude in this study is normal. Let's look at duration, and this is a little bit tricky. We measure duration in 2 ways, using all motor unit potentials and using only the simple potentials. So in this example, mean duration of all potential is 8.95 milliseconds. If you look at the simple ones, so excluding these polyphasic, the mean duration is 7.05. The normal range is 7.8 to 13. So using this, the mean duration is abnormal for the simple MUAPs. Professor Bushthal described that in patients with myopathy, excluding polyphasic potentials can increase the diagnostic yield. And therefore, we often look at the mean durations of simple potentials and mean duration of all potentials. Here is the outlier approach. We have recorded 20 motor unit potentials. The abnormal amplitude values are highlighted. In this case, we have 2 outliers out of 20, and this we will consider as normal. Here are duration values. Outliers are highlighted. In this recording, we had 20 potentials, 5 are abnormal or outliers. So this is an abnormal study based on outliers. In quantitative analysis, we often like to make summary plots such as this. Here are recordings from a normal muscle. You can see simple potentials. And at the bottom, you can see the statistics, mean amplitude, mean duration, and percent polyphasic. This is the data that we like to report. Here are potentials from a patient with myopathy, and you can see a lot of variability. You get very simple waveforms, small waveforms, complex waveforms, with late components, so forth. And once again, you can see the duration of simple MUAPs is reduced. Duration of all motor potentials is high. And in this case, 52% polyphasic potentials are noted. This often happens in chronic myopathies. And this is what happens in neurogenic conditions. You get high amplitude potentials. The mean is clearly increased, and many of these potentials are outliers based upon amplitude and durations. And therefore, we can stop the study after recording only 8 potentials. So now that we have an understanding of how the multi-motor unit analysis works, how the measurements are made, how they are analyzed, the mean values, the outliers, let's see how this is actually done in a clinical environment. The first step is to record the signals. The filter settings, as I indicated earlier, for concentric needle are about 2 to 5 Hertz, 10 kilohertz for the high frequency. The sweep is 10 milliseconds per division. This is the standard setting. We can see the waveforms for subjective assessment. The gain is about 200 microvolts per division. This is adequate in most healthy subjects and in patients with myopathy, but sometimes you may have to increase it to 500 microvolts or 1000 microvolts. We look at the signals in a free-running sweep, but sometimes you may want to use an amplitude trigger and delay line. It's entirely up to you how you want to use the program. The force of contraction is slight. This is not for analysis of the recoupment or interference pattern. As I indicated, the best results are obtained when the signal contains discharges of 3 to 5 motor units. Adjust the needle to record sharp potentials and get a signal with 1 to 5 motor units. We record the signal for 5 to 10 seconds and then let the program analyze it. So here is the display on one system. On the top, you can see a slow running suite. This is the buffer that is going to be used for analysis. The red line is the amplitude trigger. And in the bottom window, you can see the traces in the free run. Here are the sharp potentials. So this is the way you collect the data. Sharp potentials for about 5 to 10 seconds with or without amplitude trigger. There is another system. We can see the free running EMG on the top. This is at 10 milliseconds per division. The gain is 200 microvolts per division. These are sharp potentials, and we can see that from the quality meter. And at the bottom, we can see the buffer that will be used for analysis. Once the analysis is done, you need to edit the data. You need to find if something is wrong. And here are the things that we may make. We may adjust the markers for the motor unit potential duration measurements. We may delete some potentials because they are too noisy. We may combine motor unit potentials. The algorithm may make a mistake and split discharges of a single potential or a single MUAP into two motor unit potentials. And sometimes if a motor unit potential is missed, we may want to add it manually. So here is the display on one system. You can see there are 6 boxes. Here is motor unit potential number 1. This is the averaged waveform. These are the markers that are used for measuring the duration. At the bottom, you can see the firing pattern. Here is the second potential, which is selected for editing. The firing pattern at the bottom. Here are the individual waveforms. You can see the vertical cursors. They indicate the duration, and we can change them if necessary. Here is another system. We can see there were 4 different motor unit potential waveforms. The 4th one was rejected by the user for some reason. Here is the red motor unit potential that we are looking for editing. Here is the averaged waveform. Here are the individual discharges. And at the bottom, you can also see the firing pattern of the potential. And in the gray, you can see the signal buffer itself. And we can go through these buffers, look at the traces, throw them, keep them, combine them, and so forth. What I'm trying to demonstrate to you is that although we have 2 different programs for multi-motor unit analysis in our product line, the principles are essentially the same. Then we want to review our results, and this is done in many ways. We can look at a display that shows all motor unit potentials. We can look at individual motor unit potentials. We can look at the summary table that contains all the tabulated data. Or we can look at the data in a graphical manner. So here is a review on one system. We can see all the motor unit potentials over here. Here is the waveform that was excluded by the user. And even in this screen, we can change the marker positions if necessary. And in this corner over here, we have the graphical presentation of the data. Here is the summary of all motor unit potential on a different system. We can see the potentials over here. This is site number 1, motor unit number 1, site number 1, motor unit 2, and so forth. Once again, we can edit the positions of these markers. We can get rid of these traces. So for example, if you don't like this waveform, we can reject it, and so forth. Here is the tabulated way of reviewing the results. We can see the individual values of amplitude, duration, phases, turns, and so forth. The green highlight indicates that those measurements are within the normal limits. So this is where we use the outlier limits. And on top, we can see the mean values of all potentials and simple potentials. At the bottom, we have a graphical presentation of the data, which is quite similar on the 2 systems. So on the left-hand side, we have a plot. This is amplitude on the y-axis, duration on the x-axis. And each square represents measurement from one motor unit potential. And the same thing over here, amplitude, duration. There are 2 rectangular boxes that define the normal limits. So you can see the outer box, which is the bigger one. These are the limits for individual MUAPs. So perhaps a marker over here, the red one, that means this amplitude is low. And this is normal. And this duration is increased. It's in red color. It is outside this box. So the outer box is for individual measurements. The inner box shown in green over here or shown over here, is for the mean values. And in this case, we have got a lot of data points over here. This square over here represents the mean value. The triangles are the individual measurements. Once again, I wanted to point out that there is a great amount of similarity between the two algorithms. So in conclusion, multimodal net analysis is fast. It takes less than 5 minutes. It is objective. It gives us data from 20 or more motor net potentials. It gives us amplitude measurements, duration measurements, percentage of polyphasic, thickness, size ratio, and many, many measurements. It can be used for document abnormalities. Is this muscle normal or abnormal? It improves the quality of study because when you are not sure about a borderline study, at least you have a second opinion in terms of the waveforms. You can print the waveforms for reference so that somebody may be able to review them in case of doubt, or you can send it to somebody for their opinion. So this is another way I think about quantitative analysis or multi-MUAP analysis. It's a second opinion on your subjective assessment. So there is no excuse for not using it. Motor net potential is an important part. Motor net potential analysis is an important part of the EMG examination. We can do subjectively. Adding multi-motor net analysis, we get significantly more benefits, and that will improve the quality of our EMG study.